Okay, that was just a little illustration of spring tuning and what happens when you play a series of chords where you're adding and subtracting notes one by one, and the system is adjusting on the fly to try to optimize the tuning of all those sonorities to be as just tuned as possible according to small ratios as defined by whatever tuning system you're interested in using. Now, if you just want to play with spring tuning and don't really want to get into the gory details of how it works, it's very simple. Create a very simple piano like this where you connect a key map to a direct, to a tuning. Inside of tuning, under action, import, you should find autospringtune.xml. That ships with BitClavier, and so that should be there for you. You press that and it will set it this way, and you can play and monitor what's going on in the spiral view here to see and hear what's happening with spring tuning. So if you just want to play with it, don't really want to get into the details, have at it, don't need to listen any further. I'm now going to get into some of the structure of how it works, some of the basics of how it works. So if you do want to get in there and tweak and optimize or find some of the extreme behaviors you can get, you can do that. So spring tuning, I was inspired by this wonderful book by Bill Sethers called Tuning, Timbre, Spectrum, and Scale some years ago. And in it, he talked about a theoretical system proposed by John de Laubenfels many, many years ago. And in that system, de Laubenfels suggested that we could create a dynamic system where every note that is currently sounding is connected to every other note that is currently sounding by a virtual spring. And those springs would have default lengths defined by some kind of just tuning system. So major third, the spring for a major third would be 386 cents long. Okay, and you can actually see that right here. Well, it's not quite 386, and we'll see why in a moment, but it's close. And so all of those notes would be connected by these virtual springs. And as you add and subtract notes, those springs would stretch and compress in order to optimize the tuning as much as possible. So those are what we call the interval springs, the springs that set the intervals between the notes. De Laubenfels also proposed a couple other components, one of which we used, which we call the anchor springs. And the idea there is you would have sort of a phantom set, a phantom grid of reference pitches, of anchor pitches, that would also, you wouldn't hear them, but every note would be connected to the closest phantom note. So if I play a C, if I play this chord here, this triad here, or this third here, the C here would also be connected to a C right behind it that we're not hearing. But that spring would help keep that C from drifting off too far. And so if you've watched the earlier videos and you know something about just intonation, you know about the issue of drift or comma pumps, for instance, where a tuning system can become unmoored and just sort of drift away into madness. And we'll see some of that here. It's actually quite delightful. But the anchor springs serve to help hold things roughly in place. So I have a C there, I have an E here, and we'll see the E gradually return to its anchor note as the anchor spring slowly draws it close. So this keeps it from going too far. equal tempered C in this grid. That background grid is defined by this top line here. The length of the springs for the interval springs is defined here. So you could set it to other tunings as well if you like. So we have anchor springs, which keep things from drifting too far, and we have interval springs, which try to keep the intervals as close to just intonation as possible. Now this whole system is defined, described in some detail in this paper that I've talked about before, this paper that looks at tuning in bid-clavier. So if you really want to get into the details, you should go check that out. But I don't want to get bogged down in that, so I'm going to leave that for now. So let's take a look at a couple examples that will help illustrate how this works a little bit. And to do that, I'm going to share this gallery. This will be linked with this video. I'm going to go to a very basic configuration. The one that I suggested loading, that auto spring tuning, is configured to work pretty well for a lot of different situations and has a lot of different parameters defined, which we'll look at in some other videos. But for right now, I want to look at a very basic implementation of spring tuning. And I'm going to play C and E again. And you'll see in this case, we expect it to be 386. But it's 391. It's slightly larger because the anchor springs are pulling those notes, the C and the E, a little bit towards that equal tempered background anchor scale. And if I release one here, they immediately retreat to their home notes. Now, one thing I can do if I want is say, actually, I really want this to be as close to just as possible. So I'm going to reduce the anchor stiffness. So now the stiffness of the anchors is basically 0. So now we're getting the expected 386. You might get some other strange behavior if you do this. So you might decide, actually, I'm going to pull this back up just so that I have a little bit of anchor keeping things from going bananas. So that's one example right there, illustrating both the anchor scale, the anchor springs, and the interval springs. Now let's take a look at another kind of interesting example. And in this case, what I'm going to do is stick a D between the C and E. And you check this out here, and you'll see that now that C, E gets pushed a little further apart because that D, we have a whole step here and a whole step here. That's a 9/8 ratio in this system. And 2 9/8 whole steps is quite a bit bigger than a 5/4 just third. So that just third gets pushed out, bigger. We actually, if we take away the third, you'll see that the expected length of that major second is 204 cents. Same here, 204 cents. Now I add the third, those get compressed, and this one gets expanded slightly. That's cool. Let's say I actually really now want to favor the third instead of the whole steps. Like, the whole steps are fine, but what I really want to hear is a third as close to just as possible. Well, what I can do is say, I want some intervals, those springs, to be stronger than others. So what I'm going to do is make the major third, watch this, as I adjust this, I'm going to make the major third stronger, and you can see that interval compress, and I'm going to make the major seconds weaker. Okay, so it compresses even more. I can do this, and basically design, it's basically a kind of temperament where we're favoring certain intervals over other intervals. So that is really, with those two examples, you have the core concepts of how spring tuning works. With the tuning system, with interval springs and anchor springs that are holding things, keeping things oriented. We can also, like I've shown you, make overall the anchors stronger, and I could make the intervals weaker. So in this case, it goes right to equal temperament because the intervals are basically not, the interval springs are basically not active, So that is the basic structure of spring tuning. There are a bunch of other parameters, including drag, and then some things in here that we'll look at in a later tutorial.